Welcome to section 15.3. In this section, we're going to be looking at the concept of double integrals in polar coordinates. So we have already looked at how to evaluate double integrals over rectangular regions and over general regions D, but now we want to look at what happens when we want to evaluate over something that's a little more circular in nature. So we want to integrate a region that looks like these. So this would be like our region R. This would be the circular disk, right, with the outer edge, x squared plus y squared equals 1, this outer circle here. Or we could have something like this region R, where this time the inner circle is x squared plus y squared equals 1, but then the outer circle is x squared plus y squared equals 4, something like that. If we're trying to set up double integrals over regions like this, if we think of it in the convention of vertical and horizontal integration like we saw last time, that's not going to work out quite as well for circles just because you're going basically from the bottom half of a circle to the top half of that same circle, or going from left half to right half. And then you're going to have to solve these equations for x's and y's. In the case of this one, you're going to go from a line to a circle, then a circle to a circle, then a line to a circle, and you're going to have to set up different integrals. Like, it's a mess. So integrating these using traditional rectangular coordinates, vertical and horizontal integration, is not going to be the best way to go. So these types of regions are special cases of what we call a polar rectangle. So a polar rectangle, we'll get into more detail in a later section about why exactly these are called polar rectangles. But essentially it's because in polar coordinates, you have r and theta are the variables, where r represents the radius of the circle and theta represents that angle around the circle. R is going from A to B and theta is going from alpha to beta. Both of them go between constant bounds. So these are all numerical values, which in rectangular coordinates, that would represent a rectangle, right? If we had x going from A to B and y going from C to D, something like that. So because we're going between constant bounds, it's behaving like a rectangle in that sense. So we call these polar rectangles. And again, we'll see a more kind of formal explanation as to why that is towards the end of this chapter. So recall, polar coordinates of a point are related to the rectangular coordinates using the following equations. So we have x equals r cosine of theta, y equals r sine of theta, and r squared equals x squared plus y squared. So we can use these conversions to go between rectangular and spherical, polar coordinates. So use these instead, bounding r and theta instead of x and y, and we're replacing dA with r dr d theta. So instead of it being dy dx or dx dy, it is r dr d theta. Now notice, I'm highlighting for emphasis, there is an extra r here that gets picked up in this process. Why that is, I'll give you a kind of a quick explanation in this section, and then again we'll see a much more formal, thorough explanation later on in the chapter when we have a little more information. So changing to polar coordinates in a double integral, basically if we're converting from x's and y's into r's and thetas, we're just going to do the conversion. So instead of f of xy, it's going to be f of r cosine theta, r sine theta. And instead of dx dy or dy dx, it's r dr d theta, with r going from A to B and theta going from alpha to beta. So in terms of these polar rectangles, these polar regions, I have a little sample right here. So basically, if we're looking at the area, the dA right here, that's the shaded polar region. This length from the origin to here is r, right? So this is just the radius of the innermost circle. This length right here, as we go from inner circle to outer circle, that would be the change in r as we go from here to here across the region. So that's dr. Okay, so again, that's the change in radius from the lower end to the upper end, right? Inner circle to outer circle. Inside here, this little angle, that's going to be d theta. Okay, so that's the change in angle from the lower end of the region to the upper end of the region. So that's d theta. So that means that this length right here, this side length, it would be d theta, but if we're looking at d theta is just the change in the angle, right? The length of this segment is going to get longer and longer and longer the farther out we go. So it's d theta times this length right here, this r, that tells us how far out to go, essentially. So we get r d theta is this value right here. So if we want to find the area, the dA, for this region, if we treat it like a rectangle, then we would just get length times width, or base times height, to get the area. So dA equals r d theta and dr. So if I just rearrange a little bit, that's r dr d theta. So r dr d theta is going to replace the dA for these polar rectangles, okay, for these polar regions. So let's go ahead and take a look at an example here. So evaluate double integral over r of 3x plus 4y squared dA, where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Okay, if we were going to set this up using rectangular coordinates, we would be setting up integrals either vertically or horizontally between circular equations in x and y, and then these linear equations down here. In polar, all we need to consider are the radius and the angle. So in polar, our region R is going to be the set of all points r comma theta. This is a circle of radius 1. This is a circle of radius 2. Right? So we go 1 to 2. This is 0, so this would be -1 and -2. The radius of the circle goes from 1 to 2, so r is between 1 and 2. R will not be negative. R only goes out positively, so it's from here to here. And then theta is what takes us around to this side in order to cover everything. So r goes from 1 to 2, and then theta says to keep going all the way until we get to here. And that, in terms of angles in radians, would be pi. So theta goes from 0 to pi. So our double integral over r becomes, let's see, actually I'm going to put this on the next line because it's a little long with the conversion. We're going to convert all of the x's and y's into polar coordinates. So that's 3r cosine theta plus 4r r squared sine squared theta, r dr d theta, where r is going from 1 to 2 and theta is going from 0 to pi. So we're going to have to brush off our trig for this section, and you'll see that we're going to be doing many sections going forward that do involve other forms of trigonometry, particularly sines, cosines, tangents, that kind of stuff. So if you're a little rusty on it, never a bad time to go back and just review a little bit. So if we evaluate the innermost integral with respect to r, we can go ahead and let's go ahead and distribute this r into here. So that's going to be an r squared, and that's going to be an r cubed instead. Now, if we take the antiderivative, so undo, that's going to be r cubed cosine theta plus r to the 4th sine squared theta, evaluated from 1 to 2. The thetas are treated as constants because they are not being integrated at the moment. So I get integral 0 to pi. With 2, that's going to be 8 cosine and 16 sine squared, minus 1 cosine and 1 sine squared. So that's 7 cosine theta plus 15 sine squared theta d theta. And then we get single variable, single integral, like in Calc 1. You got to do a little bit of work with this one. Integrating sine squared as is doesn't quite work. We would need to use like a trig identity to rewrite that. So you saw some methods in Calc 2 of how to do trig integrals like this. Or you could even just set up using like a half or double angle identity to rewrite this in terms of sine or cosine, and then evaluate that going forward. But I'll just give you the final value here. We end up getting 15 pi over 2. So 15 pi over 2, that is the value of the double integral. And if we had not converted to polar, that still would be the answer, but we would have to somehow get that using x's and y's and the square roots of the circular equations and all that kind of stuff. So definitely a much faster, simpler process with polar coordinates than with Cartesian or rectangular. Let's take a look at this next example. Find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. So I've got the 3D graph here and obviously the 2D region as well, but just by looking at this, we have z equals 0 and z equals 1 minus x squared minus y squared. If we look at the intersection of these two, so we get 1 minus x squared minus y squared equals 0, which is just x squared plus y squared equals 1. So intersection is a circle. So in terms of the solid lies below the paraboloid. So the solid lies below the paraboloid. And above, not just the circle, because the circle is just this outside edge here, but over everything inside of the circle. So that's a circular disc. So above the circular disk x squared plus y squared less than or equal to 1. So it's everything inside of that circle. So in terms of our region R, this is inside of a circular disk, so we're going to go ahead and convert to polar. R here starts at the origin, and it hits everything until we get to the outer edge, which is the circle of radius 1. So R is going from 0 to 1, and theta starts here at 0, and it goes all the way around until we get back at 2 pi again. So theta is going from 0 to 2 pi. So the volume of the solid, this is the double integral over R of 1 minus x squared minus y squared dA, which in polar coordinates, we go ahead and convert. Now, we have a little bit of a shortcut here. Instead of converting with r cosine theta and r sine theta, notice if you factor out the -1, this is just x squared plus y squared. X squared plus y squared is just r squared in polar coordinates. So this is just 1 minus r squared. You would also get there if you plugged in r cosine and r sine directly, but it's just a little faster if we recognize that property. R dr d theta, with r going from 0 to 1, theta going 0 to 2 pi. Now, an interesting thing that we can actually do here, because we have all constant bounds here, and we have this is all a function of r, and there is no theta in here at all, we can employ one of the properties we saw that was a result of Fubini's theorem that said if you have a product of a function of one variable times a function of another, we can split the double integral into two singles. So we're going to split out the d theta integral, so 0 to 2 pi. Now there were no thetas in here, so that means it's just times 1 times the integral from 0 to 1. I'll distribute in the r, so that's r minus r cubed dr. This integral, when we evaluate, gives us that's theta evaluated from 0 to 2 pi, which is just 2 pi minus 0, so just 2 pi. So we end up with just 2 pi times the integral with respect to r. The reason that I bring this up in this process is that this happens so frequently that we kind of give it its own name. So this happens so often. We call it the theta trick. So the theta trick basically says if you have a function of just a bunch of r's and there are no thetas in here at all, the integral from 0 to 2 pi d theta will just turn into a 2 pi out in front. Okay. Now, word of caution, if these bounds are not 0 and 2 pi, it doesn't quite work the same way. Like if this was 0 to pi, this would be pi. If this was 0 to pi over 4, it would be pi over 4. If it was like pi over 4 to pi over 2, then we would have to subtract and we would get pi over 4 out of that. So, we have to be careful that the bounds are appropriate and that there are no functions of theta in here. But given this situation where you do have 0 to 2 pi d theta, we can just skip over the solution of this integral and just jump straight to the 2 pi. And again, that's just using what we call the theta trick to simplify a step that does repeat itself a lot throughout many of these types of problems. From there, so it's just 1/2 r squared minus 1/4 r to the 4th from 0 to 1, all times 2 pi. We end up getting pi over 2. So the volume under that paraboloid and above the xy plane is pi over 2. So all of these polar regions we've looked at so far, we've called them polar rectangles because they all have constant bounds and they all behave like rectangles do in rectangular coordinates. What we're going to look at next is what happens when you don't have all constant bounds for a polar region. So if f is continuous on a polar region of this form, with theta going from alpha to beta, but r going between two functions of theta instead of just two constants, the double integral will be rewritten as f of r cosine theta, r sine theta, r dr d theta, with r going from h1 of theta to h2 of theta, and theta going from alpha to beta. So just like we saw in the previous section, the integral with the variables goes on the inside, right? Constants go on the outside. And we just evaluate between two functions instead of between two numbers. So this doesn't really change anything about how we integrate these types of problems. It does affect how we set up these types of problems. So if we look at the next example down here, find the volume of the solid that lies under the paraboloid z equals x squared plus y squared, above the xy plane, and inside the cylinder x squared plus y squared equals 2x. So as you can see, we're looking at this region in here. So it's below the paraboloid, it's inside the cylinder, and it's above the xy plane, right? Above z equals 0. So that's the region in question. In terms of where this region is, without the benefit of a graph necessarily, we would need to play around with this a little bit. What we could do is subtract over the 2x, and then complete the square on the x's. This ends up giving us x minus 1 squared plus y squared equals 1. Because the region that we're working on is down here. It's this circular region. But it's not centered at the origin anymore. So D has a boundary circle of radius 1 centered at not the origin, but rather at the point 1, 0. So if we look, I've got that graph right here. So this region is this region. So what we can do in polar coordinates is we're going to go ahead and convert. Now, even though this is still a circle, it looks like it's a polar rectangle like the other ones. However, polar coordinates are centered at the origin. So if I were to say that r is going from, in this case, I mean, it would be like 0 to 2 out here. If I kept the radius going from 0 to 2 constantly, that value would be out here. And actually, I'm cutting it a little short. It would be out like here, and it would be out like way down there somewhere. So it would be giving us all of this space too, in addition to what's in this circle. So we can't just say the radius goes from 0 to 2. Okay? And we can't say that the radius goes from like 1 to 2 because, again, that would have us going from 1 to 2 like out this way, and it would be giving us all that space. So everything about polar coordinates is centered at the origin. So we have to be careful when the circle has moved away from the origin. So we're going to go ahead. So in polar, take the x squared plus y squared equals 2x. And convert. X squared plus y squared is r squared. 2x is 2r cosine theta. And then that gives us r equals 2 cosine theta. So this is the equation of that circle. So in terms of our region, D, in polar coordinates, R, like I said, is not going from 0 to 2 because that would imply that it's going from 0 to 2 everywhere. The outer value is 2, but we want to be able to get a radius that goes to here and to here and to here and to here, etc., etc. And it hits all these different values going around the circle, and these are all different radius lengths. So we want r to go from 0 up to this circle, so 2 cosine of theta. So r is going from 0 to this outer circle, okay, and that value will change depending on where we are. And then for theta, again, the temptation is to try to let it go from 0 to 2 pi, because we're thinking like this. But theta, again, starts at the origin. So this is theta equals 0 here. But as we swing theta around, the shape ends right here. Right? This is where we encompass the entirety of that circle. And then same thing down here. If we cut it off right there, our entire circle is included from this lower axis to the upper axis, like that. And that's not going to be 0 to 2 pi. This bottom value, this would be 3 pi over 2. And this top value would be pi over 2. Now, for the sake of avoiding confusion, you could do this as 3 pi over 2 to pi over 2, but people don't really like having 3 pi over 2, the larger number on the bottom. So instead, we'll just count this going backwards as negative pi over 2. Right? Because that's the same angle. But people just generally feel more comfortable with the smaller number on bottom. So we're going to say theta goes from negative pi over 2 to pi over 2. So our volume, double integral over d, it's the volume under the paraboloid, so that'll be x squared plus y squared in the integrand. So we're going to get r squared, r dr d theta, with r going from 0 to 2 cosine theta, theta going negative pi over 2 to pi over 2. We can't use the theta trick here because even though there are no thetas in this right now, we are going to be getting some in this bound because these are going to get subbed in here afterwards. So we can't use the theta trick. That integral does have to stay intact. That trick, remember, is just a byproduct of Fubini's theorem, which only works with all constant bounds. So can't use that one here. So this becomes r cubed, which when you take its integral is 1/4 r to the 4th from 0 to 2 cosine theta d theta. So we get negative pi over 2 to pi over 2. That's 1/4. 2 to the 4th is 16, so that's just 4. And then cosine to the 4th of theta d theta. The process of solving this integral with cosine to the 4th in it, it gets really messy and involves some different trig properties to do that. So I wouldn't worry about this one. It's a little more complicated than anything that I would expect you to do. If you want to try and like brush up on your trig properties and all your identities and stuff like that, that's great. You can try it. I will tell you that you should get 3 pi over 2. So it does work out pretty nicely. It just takes a little bit more work to get there, to get to that point. So we don't need to worry too much about that. The main idea of this problem is just the concept of evaluating a double integral over a region that is not centered at the origin anymore. Like we have, again, this circle, this circular disk that has been shifted over by a unit. And so we have to adjust our work accordingly because, again, polar coordinates are centered at the origin. So if our polar rectangle is not centered at the origin, we're going to have non-constant bounds. We're going to have variable bounds that we have to take into account. But that brings us to the end of section 15.3. And that is kind of the end of our introduction to double integrals. In the upcoming sections, we're going to be looking at different like uses of double integrals, and we're going to start going up one more level into a triple integral. We'll see what that looks like as well. But we will get to all of that in the upcoming sections, and I will talk to you all then.